Hello, my name is Bediako and I work with CSI, Building and Road Research Institute. Today I present on the topic entitled Decarbonizing Concrete for Sustainable Development, a focus on clay Pozzolan concrete. So to the background, sustainable development was introduced in 1987 by the United Nations under the Brundtland Commission. Dr. Brundtland was the former Prime Minister of Norway. So her definition on sustainable development was any development that meet the needs of the present without compromising the ability of the future generation to meet their own needs. So the needs of the future are captured as issues that are very beneficial to the environment, economic and social problems. So people call these things the triple bottom line. Sustainable development remains a top priority for the member states of United Nations, and we know that as of now, the United Nations have produced a document called Sustainable Development Goals. Greenhouse gases are a very important issue when it comes to sustainable development. We know that they govern global warming. These gases are global anthropogenic gases. It means that they are caused by human activities. Example of these gases include carbon dioxide, water, methane, NOx, and sulfur dioxide. All these gases are benchmarked or measured against the carbon dioxide, and we call it the carbon dioxide equivalent. As of 8th of March, I picked the carbon dioxide concentration on Earth, and we are having a daily average of over 415 parts per million. So the trend of carbon dioxide emission before 1950 were doing below 300 parts per million, but now we are rising and rising and rising. After 1950, which was characterized by industrial revolution, we saw a rising in carbon dioxide emissions or carbon dioxide concentration in the atmosphere. So there is a relation between the concentration of carbon dioxide and the temperature on Earth. So in 1880 we were lower, half the Earth was having about 0.1 degrees Celsius. In 2019 we've risen up to about plus 1.1 degrees Celsius. So you see that as the concentration of carbon dioxide increases, the temperature on Earth also increases. Climate scientists are warning against the increasing content of carbon dioxide content in the atmosphere. So they are saying that above 500 ppm, we could witness unbearable conditions on Earth. So these are some of the indicators of carbon dioxide emissions. We are having rising sea levels, cities are washed away by flooding, rising air temperature on land. It's been recorded that 2 years ago California witnessed about 54 degrees Celsius, and it created a lot of problems. Cars on the streets were melting, signages were placed at vantage points indicating that those places are no-go areas. So we have increasing temperature on sea surface. So we're seeing cyclones happening in many parts of the United States and some areas in Asia, Indonesia. So these things create an urgent need to reduce the amount of carbon dioxide entering the atmosphere. And if possible, researchers are advocating for what we call net zero emission by 2050. So the importance of decarbonization strategies have led to two billionaires speaking so much on the effect of carbon dioxide on the atmosphere. Elon Musk is one example. Bill Gates has also launched a book entitled How to Avoid Climate Disaster. All these things show that people are placing higher priority on carbon dioxide content on the atmosphere. So concrete has a relation to carbon dioxide generation. So concrete is the most widely used construction material on earth. Over 10 billion tons are produced annually, and this generates between 4 to 8% of world carbon emissions. So these are the constituents of concrete. We have sand, aggregate, cement, and water. The interesting thing is that cement generates about 80% of carbon dioxide in concrete. The 20% come from the rest of the materials. So this graph is showing some of the carbon dioxide content of some construction materials. We have stones, runs through copper, and then aluminium. It's about 11.5. So from here you see that concrete is about 0.1, which is very low. But the point is that the huge demand for concrete for infrastructure development, residential buildings, make its carbon footprint very high as compared to other materials. So one will make a case that if you had to use other materials like aluminium and steel and all these materials with high carbon content, we will create problems for the world. So the Ghanaian construction industry, we have three major issues that demand so much of concrete: population growth, urbanization, and infrastructure. And all these concrete that are used for these three major things need cement. So the trend of cement over the years from 2004 to 2020 keeps on increasing. Now we are around 7 million tons. Annually it is increasing by 6%. So the high demand for cement for infrastructure development in Ghana makes cement and concrete industry a rich target for decarbonization solution. So I have three motivations for the study. Cement industry in Ghana keeps on increasing, rising cement consumption and cost. Then we need to develop sustainable concrete to meet the growing population and urbanization of the country. We need to also explore alternative materials. Some countries are using carbon capture and storage. It is very expensive for us as a developing nation. So we can go for probably sustainable construction materials. So the main objective of this study is to investigate the carbon footprint of different set of binders used for concrete. But before I achieve that, I did compressive strength analysis, which is a mechanical property. Then I also performed the life cycle analysis of the different concrete mixes that were done in this work. So these are my materials and experimental program. Calcium cement 42.5R. The Pozzolan was obtained from BRI, coarse aggregate from the Bikini quarry. Pit sand was used and we obtained it from Drabin. And this is super plasticizer, which is not common in our concrete. In our concrete we use in Ghana. So we call it a high rainwater reducer. It is a game changer. It changes the properties of concrete. It enhances the strength and the chemistry of the concrete. So the experimental program, we did a concrete mix design using the EN 206 standard, and then we formed the concrete using the BSCN method. We performed the slump test in this work. We were working with S3. S3 means that the slump should be between 100 and 150 mm. So we performed the casting of the concrete and cure it at 37, 28, 56, and 96 days. So after all these things were done, we performed a life cycle analysis. So let me take you to life cycle analysis. Before anybody can carry life cycle analysis, you need to understand these four basic things. You have to define your system boundary, your inventory, where you're going to pick your data from, then how you're going to do the impact assessment, then interpret it. So we have cradle to cradle, we have cradle to gate. We also have database around. You can pick from. Researchers have also produced their own figures and data with respect to some construction materials. And then in this work we use carbon emission index to interpret our work. So this table is showing the embodied carbon of concrete constituent. So here we have Pozzolan cement, which was picked from the ICE database, which is 0.9500, and then we have sand, we have the admixture, the water, everything is here. So these are the results. So this is the concrete mix proportion per meter cube. So here you see the various mixes which are labeled as 0%, 20%, true to 50%. So the cement content used are here, the Pozzolan content are here, everything used in the concrete mix are tabled here. So this graph is showing the compressive strength. So the compressive strength against curing period. So 5 key things are noted from this graph. So number 1, 10% mix was 80% higher than the control at 3 days. So here is the 3 days. So what we are saying is that 10% mix. So the control line is the blue line that goes through like this, and the 10% was higher than 8%. The rest were lower. And then at 7 days, we have only 10 and 20% exceeding the control. The rest were lower than the control. At 28 days, we have 10 and 20% exceeding the control. But then you see that 30% and 40% were almost similar to the control concreteness, whereas the 50% was lower than the control mix. So what is happening at 56 days? So 56 days, we also realized that it was only 10% that was higher than the control, but then the 30 and 40% were marginally lower than the control mix, and then you will see that 50% was also lower than the control mix. And then at 90 days, the 10 and 20% had a superior strength than the control. But you can also see that 30% concrete mix was almost the same like the control concrete. However, 40 and 50 were all lower. They were trailing below the control. This graph is very important. So the zero line is defining the characteristic strength. Let me state that the characteristic strength that was used for this work was 30 megapascals. So it has been normalized against the other strength. Now this blue line is the 3 days curing period, and all the concrete mixes were lower than the characteristic strength. 7 days, it was only 10 and 20% that were higher than the characteristic strength. 30% was marginally lower than the characteristic strength. 40 and 50% concrete mix were all lower than the characteristic strength. However, at 28 days, 56 and 90 days, they were all higher than the characteristic strength. It is important to note the 50% Pozzolan content of concrete. It was a little higher than the characteristic strength. So this notification is very good for us. So let's look at the life cycle analysis. The graph is plotted between concrete mix and the kilogram carbon equivalent per meter cube. So these are the key points you have to note from this graph. Number 1, the highest emission was the OPC concrete. So this is the OPC concrete. It means that it doesn't contain any Pozzolan. That was very high, around 400 kilogram carbon equivalent per meter cube. And there was a progressive reduction of carbon emission with increasing Pozzolan content. So here, as Pozzolan increased from 0 to 50, the carbon dioxide content were decreasing. So they were all decreasing. Again, there was also marginal emission of other constituents compared to OPC. So the other constituents, that is coarse aggregate, fine aggregate, and water, they were marginally, the difference weren't that much. The difference between the OPC and the other constituent was not that much. So you can see compared to the OPC. And then as the pozzolan also increased, the carbon content of the other constituents were also increasing. So you see, it started very low, then here it was increasing, here it was increasing, it was also increasing as pozzolan content was also increasing. So we also perform the carbon dioxide emission and the total emission index. So we index the carbon content against the 28-day strength and the 90-day strength. Now the point of interest is that the blue one is showing the total embodied carbon, so the total carbon content of the material, and then the index is showing the index is the orange color. So look at the trend. So this the 0% is without the pozzolan, but then you realize that as we incorporated the pozzolan content, both the total embodied carbon and the total carbon indices were decreasing, and the decrease was very high when the pozzolan content was also high in the concrete mix. It was very similar to what happened at 90-day curing period. So after all these things were done, we tried to practicalize the mix. So we mounted this cutter, a concrete cutter, on this stand, and this stand was a concrete mix containing 50% pozzolan and 50% cement, and it was a C30 concrete. So these are the conclusions I made from this study. Number one, the binder made using 50% cement and 50% pozzolan obtained compressive strength of approximately 32, 34, and 30 MPa at 28, 56, and 90 days of curing. So what I'm saying is that these results were higher than the characteristic strength of 30 MPa. Number two, the embodied carbon of different concrete mixes progressively reduced with increasing pozzolan content in a cubic meter of concrete. The OPC had an embodied carbon of 399, whereas that of the 50% concrete mix, which was the lowest among the concrete mixes, was 222 kilogram carbon equivalent. So the third one, when we consider transportation scenario, it actually increases the total carbon emission of the product. And then the fourth one is this: the carbon emission indices of pozzolan concrete mixes at 28, 56, and 90 days of curing were lower in the pozzolan concrete than the OPC concrete. So these are some of the recommendations I made from the study. In the future, we're going to look at some mechanical properties that include flexural strength, static and dynamic modulus. We've procured an equipment that can do that. We call it the ultrasonic pulse velocity equipment. Then we will also perform durability tests. We will look at transport mechanism. We use an equipment called rapid chloride permeability test to look at the chloride movement in the concrete. Then we have an equipment called surface concrete resistivity, where we also use to look at the property of the concrete. So these are some of the references that I used for the study. I want to thank you very much, and you can ask any question bothering your mind.